This call is now being recorded.
Yeah, good evening, my dear students. Yes, today class is lecture 2 on DC motors. So here the basic types of DC motors are, there is two types of DC motor, brushed DC motor and brushless DC motor. So in brushed DC motor, there are two types of DC motors based on their excitation, methods of excitation. Based on their methods of excitation, separately excited DC motor and self-excited DC motor. As previously we studied in DC generator, different types of DC generator. Similarly, in separately excited DC motor and self-excited DC motor. In self-excited DC motor, there are three types of motor: series wound DC motor, shunt wound DC motor, compound wound DC motor. That compound one means combination of series and shunt. So here series motor, a basic definition of series motor is the series field winding is in series with the armature winding. Then that motor we can call as a series motor. Similarly, the field winding is connected in parallel with the armature winding. That motor we can call as a shunt motor. There is a combination of series and shunt. That motor we can call as a compound motor. So what is the basic differences from these motors means? So based on applications, we are going to be used as in these three types of motors. Generally, in shunt motor, we are going to be shunt motor develop constant torque. Series motor develop high torque. So here compound motor will develop moderate torque. Based on types of applications, we are going to be design the motors. We are categorize the motor, series, shunt, and compound motor. So and also in construction wise, series field winding is having less number of turns with thick wire. While coming into shunt motor, the shunt field winding is having more number of turns thin wire. So these two combinations we are going to be used in a case of compound motor. So this is the basic differences of different types of DC motors. So coming into DC shunt motor. So basic equation according to Kirchhoff voltage law, we can take as V is equal to EB plus IRA. So this IA current will be here actually IL current we are going to be taken from the supply system. That current will be flows into armature and shunt field winding. Then IL current is equal to IA plus ISH. Then if you want to find out the ISH current, that is nothing but shunt field current. The supply voltage is parallel to armature and shunt field winding. For that, here we are going to write down according to according to Ohm's law, ISH equal to V by RSH. So if you want to get back EMF from this equation, so EB is equal to V minus IRJ, including armature reaction drop and brush contact drop. So similarly, here see that this shunt field winding is in parallel with armature. Then it is called as a shunt motor. Next, coming into DC series motor, this is in a series field winding which is having less number of turns, and resistance is RA value we are going to be very less when compared to shunt field winding. In shunt field winding, the RSH value is maximum value, that is nothing but nearly 100 ohms. More than 100 ohms we are going to be taken. 100 ohms. So in series field winding, the armature value is RA value is RSC 0.0 onwards, 0.0 onwards, very less value. Why? Because this series field winding is in series with armature. When current flows in this series field winding, if it is having more resistance, means more copper losses will be takes place. For that, the efficiency of the machine is going to be less. So and also it will carry the more current, means automatically the turns required with the thick wire when compared to shunt motor. In shunt motor, the shunt field resistance is more and supply voltage is 220 volts. Because of that, ISH current is very less, shunt field current is very less. For that, here we are going to, the winding will be designed in this case is more number of turns with thin wire. here less number of turns with thick wire to carry the armature current. This is the basic differences. Here coming into voltage equation according to Kirchhoff voltage law, V is equal to EB plus IARA plus IRSC. So here armature resistance drop and RSC drop, both are in series. For that V equal to EB plus IA into RA plus RSC. So here only one closed path, because if this one closed path, IL is equal to IA is equal to ISC. So whatever may be the supply current taken from the supply system, that is IL, when that will be entering into the armature, one closed path means that equal to IA. Same current when enter into the series field winding, then it is called as an ISC. Means here IA, IS and IL both are equal. So that is the basic equation for this is the basic equation for DC series motor. Next, see here one important point in DC series motor. What is that? The DC series motor cannot started in no load condition. The DC series motor cannot be started in under no load condition. So why here? See the this is an a. See here it is an a. This circuit diagram. This is a basic circuit diagram. From this basic circuit diagram, when we are going to be applied supply voltage to this motor, when it is a loaded condition, if there is no load means automatically. So the current drawn from the supply mains is very high. Because of that, the motor is going to be dangerously runs at high speed. So here there is some expression. So why this DC series motor cannot be operated on no load means, here according to speed equation, N directly proportional to EB by pi. It is in a basic speed expression. So here IL is equal to IA is equal to ISC means the flux produced in this field winding is proportional to the supply current. Suppose there is no load means the load current is very less. A small amount of current is drawn from the supply means to overcome the no load losses. That is nothing but iron losses and rotational losses. Because of that small current drawn from the supply means the small current is entered into the series field winding. Because of the small current entered into the series field winding, the flux developed is very small. When this flux developed is very small, in the sense automatically the speed of the motor is dangerously high. The speed of the motor is dangerously high in the sense automatically the motor is going to be damages. That's why we can never operate this series motor under no load condition. Always we are going to place some load. When it is going to be placed some load, in the sense because of that load, we use some amount of current is drawn from the supply mains. So then the flux, the series field flux is proportional to the supply current. Then automatically there will be flux is some nearer to the rated flux. Then automatically we can operate the motor under loaded condition. So that's why here clearly you have to understand the DC series motor cannot be operated under no load condition. If we can operate, the motor speed is going to be dangerously high. To limit that such a speeds, we are going to place some load on the motor. Then we are going to be operated. Yes, that is the one more important point regarding DC series motor. So coming into DC compound motor. DC compound motor. So here DC compound motor, there are two types of DC compound motor, long shunt compound motor and short shunt compound motor. So in again the compound motors also we are going to be categorized cumulative compound motor and differential compound motor. So first of all we are going to be discuss here long shunt and short shunt. See here it is in a long shunt compound motor. Why it is called as a long shunt means the shunt field winding is combination of armature and series field. So means here shunt field winding provides in a long winding. Long. Why? Because why it is called as a long in the sense it is a combination of in parallel with armature and as well as series field winding. That's why this motor we can call as a long shunt motor. So if this shunt field winding is connected only in parallel with armature winding. So see here it is a short shunt compound motor. The shunt field winding is connected only with armature winding. So means it is in a short. Because of this short connection, we can say that it is in a short shunt compound generator. Short shunt compound generator. Sorry, short shunt compound motor. Here it is in a long shunt compound motor. These are the basic two different types of motor, compound motors. And also here we are going to be discuss cumulative compound motor and a differential compound motor. So what is the cumulative compound motor and what is the differential compound motor means? Here in this both motors there is a series field winding and shunt field winding. There are two fluxes here. Total flux developed in this motor is equal to both cases, either may be long shunt, either may be short shunt. So pi sh by pi sh plus phi sc. So plus means here we are going to be given such a way, we are going to be given here connection such a way that the series flux produced in this series field winding added with shunt field winding, then the resultant flux is going to be increases under load condition, under loaded condition. Such a motor we can call as an cumulative compound motor because of this cumulation will be takes place here phi ss and phi sc. Both fluxes are added together. Such a motor we can call as a cumulative compound motor. Either may be long shunt, either may be short shunt. So coming into differential compound motor, simply instead of here we are going to be interchange the series field connections. Series field connections reversed automatically. The series field flux produced from the series field winding opposes to the shunt field winding. Then automatically instead of plus here we are going to take as a minus. So phi sh opposite to the phi sc opposite to the phi sh. Then resultant flux is going to be reduces. So this motor we can call as in a differential compound motor. So here what is the basic differences between differential compound motor and cumulative compound motor? Here in compound motors there are two types of winding connection. One is shunt field connection, another one is series field connection. Both field connections are connected with respect to armature such a way that this both fluxes are added together. The resultant flux is going to be increases under loaded condition. This type of motors we can call as a cumulative compound motor. So here this both fluxes are the shunt field flux and series field flux opposite direction. Once we reverse the series field flux connections, automatically the series field flux produced from this compound motor opposite to the shunt field connection. Automatically the resultant flux developed under loaded condition is going to be reduces. This motor we can call as this type of motors we can call as a differential compound motor. So that is the basic difference between differential compound motor and cumulative compound motor. So coming to here, next topic is motor characteristics. So what are the basic three types of, there are three types of characteristics: torque and armature current characteristics, speed and armature current characteristics, speed and torque characteristics. There are three types of characteristics for a series, three types of characteristics for all the motors. So here basic expressions we are going to be understand to understand these topics. One is torque directly proportional to phi Ia and n directly proportional to Eb by phi. Already we know that this equations, torque equation, T directly proportional to phi Ia and n directly proportional to Eb by phi. So first of all here we have to see the DC shunt motor characteristics of DC shunt motor. So first characteristics, torque versus armature current characteristics. Torque versus armature current characteristics. For that we know T directly proportional to phi Ia. So phi and Ia. In shunt motor, the shunt field flux is constant. The shunt field flux is constant. Therefore, T directly proportional to phi Ia. So means when load is increases on DC shunt motor, the current drawn from the supply mains increases. That is armature current also increases because of this torque also increases. So that's why here there is a linear characteristics. T versus Ia characteristics, linear characteristics. So T directly proportional to Ia. When load increases, armature current increases, torque developed on DC shunt motor also increases. So now coming into armature current versus speed characteristics. Now armature current versus speed characteristics. Already we know that N is directly proportional to EB by phi. Here flux is constant. When flux is constant, then N directly proportional to EB. Already we know that basic equation EB is equal to Vt minus IRA. Back EMF developed on DC shunt motor. Now N directly proportional to Vt minus IRA. So when load increases, there will be increment of IRA drop. Because of the drop will be subtracted from supply voltage, there will be a small reduction in speed. There will be a small reduction in speed. So for that we are going to draw on the speed versus armature current characteristics. So when we neglect this small drop, automatically we can say that the speed characteristic of this shunt motor is constant speed characteristics. So this when load increases, load current increases, the speed of the motor is decreases a smaller value, that is nothing but IRA. Why it is in a smaller value? In the sense the armature resistance of the DC shunt motor is small. Because of this product of armature resistance into load current, that value will be very small. That's why we can say that shunt motor is having constant speed characteristics. Next, speed versus torque characteristics. Here instead of here T directly proportional to phi Ia. Yes. So instead of T, we are going to place it as an Ia. Or in this case, torque versus this is a torque here as an Ia. Already we know that T directly proportional to Ia. So instead of Ia here only we are going to be taken as an torque. So here. So from that we are going to understand it is having again the speed and torque characteristics also constant. Next, coming into characteristics of DC series motor. So again we are going to be understand the basic equation, that is nothing but T directly proportional to phi Ia. But here T directly proportional to phi Ia, when load is changes on DC series motor, the load current also changes. That series field flux also changes. This flux also changes. So in a case of shunt motor, this flux is constant, but in a case of DC series motor, this flux is directly proportional to load current, that directly proportional to armature current. So for that reason, we are going to say that, so T directly proportional to phi Ia, Ia directly proportional to phi. That's why we are going to write down T directly proportional to Ia square. T directly proportional to Ia square here. So see here, when we draw the characteristics, it's in a parabolic characteristics. See here. So when armature current load increases, load current increases, because of that armature current also increases. Then torque increment is T directly proportional to Ia square. So these are the torque versus armature current characteristics of DC series motor. So coming into speed versus armature current characteristics. Speed versus armature current characteristics. So here, what is the speed equation? N directly proportional to EB by pi. So N directly proportional to EB by pi. Suppose under no load, the current run from the supply mains is very small. Because of that, flux developed also very small. This value flux developed is very small. This flux is inversely proportional to speed. Because of this small flux, the motor is going to be runs at higher speeds somewhere else. This is the point, starting point. Because of here, it is in a current. Here, see here, current is small. Load current is small. When load increases, load current increases. This value increases. When it increases automatically, when load current increases, same current flows through the series field winding. Because of that series field flux increases, the speed reduces. So this is the speed reduction here. When load increases, load current increases, series field flux increases, speed is going to be reduces. So these characteristics are nothing but speed versus armature current characteristics. Very, very important, these characteristics. Next, coming into speed versus torque characteristics. Speed versus torque characteristics. Instead of current, only we are going to be replaced with as a torque. But here, how the torque? T directly proportional to Ia square. So it is a hyperbola characteristics. Hyperbola characteristics. It is similar to speed and armature current characteristics. Next, characteristics of compound motor. Characteristics of compound motor. Cumulative compound motor. So cumulative compound motor in the sense, under no load condition, the series field winding carries less flux. Because of that less flux. So initially T directly proportional to phi. Actually T directly proportional to phi. The directly proportional to phi SH plus phi SC. So this shunt field flux is constant. Shunt field flux is constant. When load increases, the current flowing through the series field winding is increases. Because of this increment added to the shunt field flux, total flux is going to be increases. Total flux increases and also current increases. So for that reason here the cumulative characteristics are like this. In differential characteristics, this phi s is opposite to minus. Instead of plus, here minus. The series field flux is opposite to the shunt field flux. Net flux is going to be reduced. Net flux is going to be reduces. When net flux is reduces, automatically the torque is going to be here. See the comparison between cumulative and differential. Both fluxes are added because of this one. The torque is increases. Here the torque is decreases. When load increases, load current decreases. Next, speed character. It is a constant speed characteristic similar to the shunt motor. Suppose in differential compound motor, the flux is going to be, already we know that basic equation, N directly proportional to EB by pi. Yes, right? Because of differential, flux reduces, speed increases. This is the characteristics, differential. Next, cumulative. Cumulative means flux increases. Flux increases means automatically speed reduces. This is the reaction speed. Yes, all of you understand here? Speed versus armature current characteristics. It's very, very easy characteristic. Here, see, these characteristics are from rated speed to. Why? Because there is a shunt field winding. Under no load condition, the series field carries very less amount of current. Because of that, the motor is going to be act as a shunt motor. When load increases, there is a current is flowing through the series field winding, load current. Because of that, series field flux is going to be increases. This increased series field flux added to the shunt field flux, net flux is going to be increases. In a case of cumulative compound motor, the speed is going to be reduces. While coming into differential compound motor, the series field flux is opposite to the shunt field flux. Net flux is reduces. This one. Then speed is going to be increases. But there is no such a type of applications we cannot see in general. Why? Because when load increases, automatically what happened in general practical cases, the speed of the motor is going to be reduces. Next, speed versus torque characteristics. These characteristics are similar to that of speed versus armature current characteristics. These are the characteristics of compound motor. See here, because of this, we are going to be chosen as an applications. This is shunt motor applications. Because of constant speed, very, very important point, constant speed and constant torque. It will be used as in a lathe machines, drillers, lifts, fans, boring mills, centrifugal pumps, and spinning machines. So while coming into DC series motor, it is best suited for high starting torque. High starting torque. So high starting torque means here which type of applications? Those are nothing but a very very important electric traction. Nowadays, the from olden days onwards, we are going to use DC series motors in traction and cranes and lifts, elevators. These are the major important applications for DC series motor. Why? Because T directly proportional to 5IA in 5 directly proportional to again IA substituted here T directly proportional to IA square. So which indicates suppose 10 amperes of load current, there will be 100 Newton meter torque will be developed. Suppose 100 amperes we are going to be given load automatically. The torque developed is 100 square, 10,000 Newton meter. That is the capability of DC series motor. While coming into DC shunt motor, suppose 10 amperes is the load current, the torque also 10 Newton meter. 100 amperes means 100 Newton meter. While coming into DC series motor, it is suitable for very very important characters, high starting torque, where it requires high starting torque. Those applications definitely we are going to be choosing as a DC series motor because of T directly proportional to 5IA. 5 is directly proportional to again IA, then T directly proportional to IA square. So suppose when we are given as in a 10 amperes of load current, the torque developed on this series motor is 100 Newton meters. Suppose 100 amperes of load current, it will be developed 100 square, that is nearly 10,000 amperes. 10,000 Newton meter. That is the uh, major advantage of DC series motor. Next, separately excited DC motor, it is similar to that of uh, shunt motor, but here we are going to be possible to adjust the shunt field current. That is the one advantage of separately excited motor. And the drawback is it requires separate DC source. It requires two sources. So armature for one source, that is nothing but we are going to be given DC supply for the armature winding, and also we are going to be given DC supply for the field winding also. That motor is nothing but separately excited motor. While coming into compound motors, here compound motors are mixed and moderate advantages. That is nothing but it acts as a shunt motor characteristics under no load, and it is having as a series motor characteristics under loaded condition. So for that reason, here we are going to be choosing as a both application combination of shunt motor and series motor, and it is also suitable especially in hoists, rolling mills, compressors, conveyors, stamping machines, elevators. We are going to use as a compound motors. Compound motors. Next topic is speed control of DC motor. Speed control of DC motor. So we know the basic equation back EMF when the motor is going to be when current carrying conductor is placed in a magnetic field. When it's carrying current automatically, this conductor is rotated in the magnetic field. When same conductor is going to be caught that flux, and EMF will be induced in this back of the armature. That induced EMF is nothing but back EMF. That is EB directly proportional to pi Zn by 16 to P by A, basic equation, just like an induced EMF equation. So from this, we are going to be obtain the equation N directly proportional to EB by pi. EB by pi. So from this equation, the speed control of DC motor is depends on back EMF and flux. When flux reduces, speed increases. That's right. When so when flux increases, speed reduces, opposite. When flux reduces, speed increases. So means here there is a change in flux, we can control the speed of the DC motor. Next, and again back EMF EB. Already we know that EB from this equation, from this V equal to EB plus IRA, from that EB is equal to P minus IA RA. So from this we are going to understand it is in a one speed control technique. This one is in a second two speed control technique, and this one is in a three. There are three types of speed control techniques. What is flux? One is flux control method, another one is supply voltage control method, third one is armature resistance control method, or otherwise armature voltage control method. There are three types of method. When the supply voltage also, it is not possible to increase more than the supply voltage. It is possible to reduce from rated voltage to less voltage. That's why here when this V voltage is reduces, back EMF also reduces. So when back EMF reduces, flux is constant, speed is going to be reduces. That is nothing but supply voltage control method. In supply voltage control method, we can obtain the below rated speeds. Here we are going to be obtain the below rated speeds only. See here, listen. All of you listen carefully. So this is a basic equation. It is a basic equation, n directly proportional to EB by pi. So here when supply voltage V is reduces, there is a possibility reduction, reduces. It is not possible to given more than that rated voltage to the supply system. So when we given automatically, there will be chances to failure of insulation. So many drawbacks are there such that we can given less than the rated voltage. It is possible. When with this supply voltage is reduces, automatically EB reduces. When EB reduces, this EB is directly proportional to N. Speed is going to be reduces. Similarly, when we are going to be adding some external resistance to the rotor circuit for this one, total IRA drop is increases. This increased IRA drop is subtracted from supply voltage. Then total EB is going to be reduces. When EB reduces, speed also reduces. So by seeing this theory, we understand supply voltage control method and armature resistance control method. Both methods we are going to be obtained below rated speeds. By using these two techniques, we are going to be obtain the below rated speeds only. While coming into flux control method, so in flux control method, it is possible to reduce the flux from its rated value. So it is not, once we design the machine, it is not possible to increase more than the rated flux. That's why it is possible to reduce this by placing some resistance into the in series with the series field winding. There is a possibility to reduction in flux in the series field winding. Then when flux is reduces, automatically speed is going to be increases. So for that reason, here we are going to say that flux control method is suitable for above base speeds only. Here we can call it as a flux control method also above base speed control method. These are the basic methods, speed control methods to control the speed of the DC motor. So see here, by varying the supply voltage, by varying the flux, and by varying the armature voltage. That is nothing but by varying the armature resistance. These are the three basic methods to control the speed of the induction motor. Now we can see these methods how will be act in shunt motor, how will be act in series motor, how will be act in compound motor. Next, coming into first one, flux control method for as a shunt motor. Flux control method for as a shunt motor. It is a shunt motor characteristics. So these are series motor characteristics. So shunt, here when we Here, see here the circuit diagram. It is in a RSH actually. When supply voltage is connected, here we are going to place as an armature resistance RA in series with armature winding. It is an armature control method. Suppose we can keep it is in a constant. We can vary this resistance in series with the shunt field winding. Then the current flowing through the shunt field winding is vary automatically. The flux is changes and speed also changes. So similarly, in case of series motor also similar, same. So these are the series motor speed characteristics. It's in a shunt motor speed characteristics. Next, armature voltage control. While coming into armature here, this one is constant varying. Shunt field resistance is varying. Here armature control method. Here armature resistance is varied. Armature resistance is varied. So these are the basic three basic different types of speed control of DC motors. Next, come to starting methods for a DC series motor. Generally, the DC motors cannot started directly. Directly, you cannot give a supply to the DC motor. Why? Because here, see here. So already we know that basic equation V is equal to EB plus IARA. From this, what is the IA? Simply V minus V minus EB by RA. So if the motor is at rest position, this EB value is 0. There is no back EMF is developed on either maybe DC series motor, either maybe shunt motor, whatever may be the motor we can use. The back EMF developed on that motor is EB is 0. Then there will be, we are going to be given as a supply voltage directly, the 220 volts, the rated voltage. So here armature resistance is, for example, taken as a 0.5 ohm. 220 by 0.5 ohm. That is nothing but 1 by 2. Nearly 440 amperes current is drawn from the supply mains. So because of this high starting current drawn from the supply mains, the DC motors is going to be damages. So for that reason here, when we start the DC motors, definitely we require starting methods to control the current drawn from the supply mains. So here, see here, you understand when at rest position, if the motor is rest position, EB is 0, then IA is equal to V minus V by RA. That is nothing but 220 by 0.5, 440 amperes. Instead of nearly 20 amperes is the rated current of DC series and shunt compound motors. Because of 20 amperes drawn at rated load condition, when we start the DC motors without starters, it will be draw a huge amount of current, 440 amperes. Automatically the motor is going to be damages. Why? Means the EB is going to be 0, back EMF. The motor is at rest position. The back EMF developed on this motor is 0. That's why huge amount of current is drawn from the supply main. That is nothing but nearly 20 to 40 times of rated current. The motor is going to be damages. For that, here we are going to be place some in series with some resistance into the armature circuit. When this resistance is increases maximum value, then automatically the IA current will be reduces. So means simply, what is the methods to use to take to start the DC motors? Means 3-point starter, 2-point starter, 4-point starter, like that we are going to use. What is the main advantage of the starters? Means these starters are placed the external resistance in series with the armature winding at starting condition. When this resistance is added in series with the armature winding at starting point, automatically the current drawn from the supply mains is going to be reduces. Because of this reason, we are going to be design 3-point starter and 2-point starter and 4-point starter for as an So it is in a starter diagram. See here. It is in a shunt motor. A1 and A2 is armature winding. F1 and F2 is shunt field winding. Here L is an A. Generally, there are three terminals are there, 3 points that are line, field, armature. With respect to that, line connected and field is connected, armature is connected. See how will be the line that will be starting. This is the diagram. Total resistance is included into the armature. While starter is, this is an a starter handle is going to be rotated from R1 to R5. Initially, armature resistance, initially starter resistance is more. When we are going to be moving that starter handle to the R5, automatically the resistance is reduces. Like that, simply we are going to be started as in a DC motors by using starters to avoid the high current drawn from the supply mains. Next topic is losses. Generally, what are the losses here? Total losses of DC emissions, that is nothing but copper losses, iron losses, mechanical losses. Copper losses, iron losses, mechanical losses. Again, the copper losses are categorized: armature copper losses, shunt field copper losses, series field copper losses. And what are the iron losses means? Hysteresis losses and eddy current losses. Mechanical losses, friction losses, windage losses. So again, these friction losses are bearing friction and brush friction. Bearing friction and brush friction. There are two types of friction losses: bearing friction and brush friction losses. See here in this total losses, copper losses, iron losses, mechanical losses. So in these losses again we are going to be taken copper losses. The copper losses here, the copper losses are nothing but armature copper losses, shunt field copper losses, series field copper loss. So again, these losses we are going to be categorized. Again, these losses are armature copper losses, shunt copper losses, series field copper losses. From these losses, we are going to be categorized constant losses and variable losses. All these losses we are going to be categorized into two types of losses. What are those two types of losses? Variable losses and fixed losses or constant losses. So what are the variable losses from these cases means? Armature copper losses are variable losses. And also series field copper losses also variable losses. So remaining all the losses we are going to be treated as in a constant losses. Shunt field copper losses means when current is flows to the shunt field winding, there is having some shunt field resistance, then there will be takes place of shunt field copper losses. But the shunt field current is constant. Why? Because supply voltage is constant, RSH is constant. Then I is equal to, what is the I is equal to? ISH is equal to V by RSH. V by RSS. Here RHS is constant, V is constant, then ISS is constant. The shunt field copper loss also constant. Next, iron losses. This iron losses depends on supply voltage. When V1 supply voltage is constant, flux developed on DC emission is constant. Therefore, iron losses is constant. This iron loss is constant. This iron loss is categorized into eddy current losses and hysteresis losses. Eddy current losses. What is meant by the eddy current losses? When armature is rotated, the rotor of DC machine is rotated. When this armature is rotated, the main field flux is going to be cut the armature conductors and EMF will be induced. That is our required EMF or useful EMF. In addition to that, the core of the armature also cut the flux, main field flux. Because of this, there will be EMF induced in the core of the armature according to Faraday's laws of electromagnetic theory. This induced EMF drive current through the core of the armature. Those currents are nothing but eddy currents. These eddy currents will give us as an eddy current losses. Similarly, hysteresis losses. Hysteresis losses. What is meant by hysteresis losses in the sense? Suppose when the armature is rotated, this armature is going, the flux, main field flux flows from north pole to south pole. When this armature is rotated, in this armature, sometimes flux is flows from north pole to south pole in the armature, sometimes always north pole to south pole. When the armature rotor is rotated automatically, there will be a reversal of flux is flowing through the armature, core of the armature. Because of this, some amount of power is going to be spent. That power is nothing but hysteresis power. That loss we can call as an hysteresis losses. So here there are two types of iron losses. One is hysteresis losses, another one is eddy current losses. Next, mechanical losses. What is the mechanical losses? Are rotational loss. This loss also we can call as a rotation. Because of rotor rotation, this loss are takes place. Windage loss and frictional loss. What is meant by the windage loss in the sense? There is some air gap between the rotor and stator to provide rotation for the rotor. When this air gap will be filled with air automatically, when rotor is starts rotating, this air is going to be opposite to the rotor rotation. For that, some amount of power is going to be drawn from the supply means to overcome this opposition. That power we can call as a windage power or windage loss. Similarly, friction and bearing friction and brush friction. Because of this friction exists, there will be heat is developed in the bearing friction and brush friction. So there will be some loss will be takes place in the bearing friction and brush friction. Those losses we can call as a frictional losses. These are the losses regarding DC missions. So here the speed of the suppose when we are going to be taken as a shunt motor, this mechanical loss also, the speed of the motor is constant. This mechanical loss also constant. Iron loss is constant. And what are the constant losses in DC shunt motor means iron losses, mechanical losses, and shunt field copper losses. So what are the variable losses in a case of shunt motor means armature copper losses, series field. There is no series field winding in shunt mission. So only armature copper losses is the variable losses. Next, coming into series motor. Series motor. So iron losses are constant losses. What is the variable losses in a case of series motor? Armature copper losses, series field copper losses, and also rotational losses. There will be some speed drops here more when compared to shunt motor. For that reason, here we are going to say that these losses are variable losses. What are those losses? Mechanical losses, armature copper losses, and series field copper losses. So in this case of series motor, only iron losses are the constant losses. Remaining all losses are variable losses. Next, this combination we are going to be understanding in a case of compound motor. Suppose all these losses are definitely exist in compound motor. So suppose we can say that these losses we are going to understand in all the compound motors. So how we are going to be categorized these losses? Generally, in compound motor also we can call as in a constant speed motor. So for that reason, this mechanical losses are constant, iron loss also constant. From no load to full load. From no load to full load, iron loss are constant and mechanical loss also constant. For that reason, we can say that these fixed loss are nothing but iron losses and mechanical losses in a case of compound mission. And also shunt field copper losses also constant. Then what are the variable losses? Armature copper losses and series field copper losses are the variable losses in in a case of compound missions. This is entire theory regarding losses in DC missions. Yes. So same points are there here. Copper losses and iron losses. Next, what are the tests we are going to be conduct in DC motors? That is nothing but brake test and Swinburne test, retardation test, and Hopkinson test. So some types of tests we are going to be conduct to evaluate the performance of DC missions. To evaluate the performance of DC missions, we are going to be conduct test on DC missions. Especially the main test is Swinburne test. Swinburne test. So here a spin burn test we can call as a name. This spin burn test we can say that no load test. Generally there is no load is required for this test. Simply we can operate the mission under no load condition. Only we are going to be evaluate no load losses. We are going to find out no load losses from this spin burn test. And predetermination we are going to be taken as an approximate load currents. From that we are going to be calculate the copper losses. Then we are going to be evaluate efficiency. See here what is the efficiency. Efficiency already we know that the efficiency of any machine is output power by input power. Input power is nothing but output power plus losses. Here what are the losses? Variable losses plus constant losses. Variable losses plus constant losses. Now we are going to be calculate. Now we are going to be taken as in a shunt motor. Shunt motor. Here this field winding is in parallel with armature winding. Here to measure the no load current, here 1 meter is connected in series with the line, supply line, and 1 meter is connected in shunt field winding. When we can given supply 220 volts DC supply for this motor, then the motor is going to be operated rated. Then the motor is going to be operated at rated speed by adjusting a speed and field restart and armature restart. The motor runs at rated speed. Then the note down the meter readings, shunt field meter reading and supply meter meter readings. And also we can measure the supply voltage 220 volts. From this we are going to be calculated no load losses, that is nothing but V into I naught. I naught is no load current, V is supply voltage. So here RA square into that is nothing but what is the IA square into RA. IA is nothing but I naught minus ISH, shunt field current minus line current, I naught current. Then we can obtain the constant losses. Constant losses. Next, then armature current. IA is I minus ISS. I is the load current. IS is shunt field current. Then see here input power V into IA. Armature copper losses. IA square RA. From this we can obtain armature copper losses. And also we know WC constant losses. Then efficiency of the motor. Input minus losses. It is the input power V into I naught. No load input power. Suppose load, we are going to be taking some assumption. I is the full load current. That is the input power V into IL. Then here I square RA, copper losses. These are the constant losses by input power. Simply you can, from these expressions, we can obtain the efficiency of DC motor at any particular load current. You can just simply you can change this current value in copper losses and as well as input current. Automatically we are going to be obtained. So generator. Already we know that generator efficiency of running as a generator. Output power by output power plus losses. Here we don't know the input power because of generator. Why? Because here generator we are going to be given as a mechanical energy is the input. We know the output here, that is VLIL. So for that reason here we are going to write down VLIL is an output power, and here instead of input power we are going to take an output power plus losses. We know the output power VL into IL and losses. What are the losses? Variable losses and constant losses. Next, see the merits and demerits of this test. Since this test is no load test, power required is less, hence the cost is economic. The efficiency of the machine is found very easily because the constant losses are well known. This test is appropriate only. Next, coming into demerits. When DC machine is loaded, this test does not deliberate the stray load losses. That is, stray load losses occurs. By using this method, we cannot check the DC machine performance at full load condition. These are the demerits, and also one more demerit. This test is not applicable for series motor. Why? Because series motor is not possible to operate on no load condition. This Sinban test is conducted either with compound motor and shunt motor only. This test is not suitable for series motor. So this is the today class topics regarding gate point of view. Thank you all of you, those who are actively participated in this session. Please all of you leave from the session.